So today we're going to talk a little bit about perpendicular bisectors within a triangle. If you're looking at this, chances are that you've already learned how to construct just a perpendicular bisector of a segment. So for instance, segment MN here, I'm going to construct its perpendicular bisector. The way I do that is I put my compass tip on one endpoint, open the compass so that it's between halfway and all the way across. Sometimes 2/3 of the way across is mentioned as a good idea. And make an arc. Now I'm going to move my compass tip to the other endpoint and make sure I make the same size arc. Sorry, my arc's a little squiggly at the top there. But the idea is that my two arcs cross in two places. So that's why I'm not too worried about that squiggle, is because I can still see where they intersect here and here. Now every single thing on this arc is an equal distance away from N, because it's like it's a circle or a piece of a circle with a radius from N. N is the center, and whatever the radius is of your circle, it stays the same all the way around the circle. Similarly, everything on this arc is an equal distance away from M. So these 2 points are an equal distance away from both M and N. And when I connect them, I get a couple things. I get my perpendicular bisector. That's what this line here is. It's my perpendicular bisector. It's perpendicular to MN, and it bisects it. It cuts it into two congruent pieces. So in other words, if I call this P, MP is the same length as PN. The other thing is, by making the perpendicular bisector, it has to go right through the middle of the segment. It has to bisect the segment. So I've also found the midpoint. So P is the midpoint of segment MN. All right, now, perpendicular bisector, well, actually it says, let me follow these directions over here. It says pick any point AB on it and label it P. So I'm going to pick, any point on AB. I never did name my perpendicular bisector AB. So let's go ahead and call it A, B. Now I called this P, I'm sorry, I wasn't following the directions. It says to call whatever point I pick. I don't want that to be the midpoint. So I'm going to pick a different point and call it P. So I'm going to pick this point down here and call it P. It says draw segments from P to M and P to N. So I'm connecting P to M, P to N, mark the segments you just drew according to the perpendicular bisector theorem. Well, that's this thing in the box. It says the perpendicular bisector of a line segment contains all points blank from the endpoints of the segment. Well, how do you think P relates in terms of its distance from M and its distance from N? We know that this point right here is exactly the same distance from both of them. Turns out every single point on the perpendicular bisector has that same property. Every single point on AB is an equal distance from M and from N. So my point P, no matter where it is, if P is here, if P is here, if P is here, if P is here, it doesn't matter where P is, every single point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment, which in this case are M and N. So in other words, this length MP and this length NP are the same. So equidistant is what goes in this blank. The perpendicular bisector of a line contains all points equidistant from the endpoints of the segment. And sometimes you will see that sort of asked backwards, because the converse is also true. For instance, let's say I have a point, say I'm going to take my segment AB. If I take my segment AB and I have a point, let's call it Z, and someone tells me, well, A to Z is the same as B to Z. And that's not perfect because I'm freehanding it. If I know that that's true, they'll say, what do we know about Z? Well, we know from the converse of the perpendicular bisector theorem that it must lie on the perpendicular bisector of AB. So not only is every single point on the perpendicular bisector equidistant from the endpoints of the segment, but any point that is equidistant from the endpoints of the segment must be on the perpendicular bisector. All right, so looking at these problems below, here's what this means for those. Number one, find EF. Okay, well, in all of these, well, actually, I was going to say we need to assume, but there's nothing, we don't have to assume anything, it's shown to us. I know that HF is the perpendicular bisector because two things are shown to me. Perpendicular and equal lengths on either side. The equal lengths on either side show that it's the bisector. The perpendicular symbol or the right angle symbol shows me it's perpendicular. So FH is the perpendicular bisector of EG. That means every single point on FH, including point F, is an equal distance from E and from G. So 2x plus 5 is equal to x plus 10. Subtract x's from both sides, and I get 1x over here, 5 from both sides, and I get 5 over here. X is 5. Is that what I was asked to find? No. I was asked to find length EF. So E to F, 2 times x plus 5, that's 2 times 5, which is 10, plus 5. So EF is 15. Remember, when you have a segment name with no symbol over the top, that means the length of segment EF. Okay, that's what that's saying. Find the length of segment EF, which is the same thing as asking the distance from E to F. All right, so you go ahead and pause the video. Try 2, 3, and 6. And pretend that's a 4. Okay, so go ahead and pause the video. Try these other 3 problems. And then turn it back on and check up and see if we got the same thing. I'll go ahead and go through these. On this one, we know that HE, since H is on the perpendicular bisector, HE and HF are going to be congruent. This gives me x is 2, and that's all I was asked for on number 2. Number 3, again, all this information tells me that MK is the perpendicular bisector of JL. So M to L is the same as M to J. So MJ is 12. And finally, this information tells me that QS is the perpendicular bisector of PR. So Q to P and Q to R are the same. 5x equals 3x plus 8. 2x equals 8. X is 4. QR is what I was asked for, so I have to go back and plug that in here. 3 times 4 plus 8 is 12 plus 8 is 20. All right, moving on. On the back, this is where we're getting into triangles. It says we can find a special point by constructing the perpendicular bisectors of all 3 sides of the triangle. So let's go ahead and do that. One at a time. First, I'm just going to focus on side EG. Make its perpendicular bisector. Open the compass a little more than halfway. And it's easiest for me to turn it upside down since I'm right-handed when I'm doing the left side. If you're left-handed, it might be easiest to turn it upside down when you're doing the right side. Notice that I'm kind of trying to keep my markings a little light. I hope you can still see them. But I'm going to have a lot of markings on this because I'm doing each side. So I'm going to do the perpendicular bisector 3 times. And I'm trying to keep them light so that they distract me as little as possible. So here's a perpendicular bisector of EG. And I'm going to go ahead and mark it as such. Well, I'm going to wait on that. Let's wait. Then I'm going to do the same thing for FG. So there's my arc from F. Here's my arc from G. And I can connect those 2 points of intersection with my straight edge. And this is my perpendicular bisector of FG. And last but not least, I'm going to do it for EF. This is where things start overlapping to the point that it's hard to tell what's going with what. So I'm just going to go back over these to make them a little darker so I can make sure I can tell what my perpendicular bisectors are. One thing to notice here is, unlike angle bisectors, the perpendicular bisector does not necessarily go through a vertex of the triangle. In other words, notice that this perpendicular bisector does not even touch E. Doesn't touch E, F, or G. Same thing here. This perpendicular bisector does not touch E, F, or G. It doesn't have to touch one of the sides of the triangle. Now, if I wanted to mark these as perpendicular bisectors, that would mean a right angle and congruent marks on either side. So I could do that for each one of them. Use different congruent marks, or a different number of them. So that's the markings I need to see to convince me I have a perpendicular bisector. In this case, 3 of them. Now mine's a little bit off. There's some human error here, but the big idea here is that these 3 lines come together in a single point, meaning they are concurrent. So this is a point of concurrency. Remember, concurrent means coming together in a single point. When you have 3 or more lines that can meet in one point. And point of concurrency means the point where that happens. So this point right here is a point of concurrency. Let's call it P. All right, well, P is a point of concurrency, excuse me. When we do, and in our class we've already done angle bisectors, we found that that was also had a point of concurrency. And with angle bisectors, that point of concurrency had a special name. Same thing here, but it's a different name. The point at which all 3 perpendicular bisectors meet is called the circumcenter of the triangle. So P is my circumcenter. It is equidistant from the blank of the triangle. Well, coming back here, we just studied the fact that everything on the perpendicular bisector is equidistant from the endpoints of the segment. So let's look at how that applies here. Everything on this line is equidistant from F and G. Everything on this line is equidistant from E and G. Everything on this line is equidistant from E and F. This point is on all 3 lines. So it's equidistant from E and F and G. Those are called the vertices of the triangle. The corners, the points of the triangle, we call the vertices. So the circumcenter is equidistant from all 3 vertices of the triangle and is the center of where the name came from is not just random, it's the center of the circumscribed circle. Circum means around. Scribed means written or drawn. So we're talking about a circle that is drawn around the triangle. Now I'm going to try to do it. Again, we got that human error issue, but I'm going to try and show you. Not bad. There is my circle that is drawn all the way around the circle so that it goes through every point, all the way around the triangle so that it goes through every point or vertex of the triangle. P is the center of that circle. So it's the center of the circumscribed circle, drawn around circle. So that means it's the circumcenter. That's why we call it circumcenter. It's the center of the circumscribed circle. Another point that goes with that is what we just said about it being equidistant from the vertices. If you look at the distance from P to F, the distance from P to E, and the distance from P to G, it makes sense that all 3 of those are the same. Why? PF, PE, and PG are all radii, or the plural of radius, radiuses. You could say if you wanted to say it wrong, but technically it's radii. Okay, so PF is a radius of that circle, PG is a radius of that circle, PE is a radius of that circle. The whole definition of a circle has to do with the fact that the radius doesn't change sizes. Every single point on the circle is the same distance away from the center, and that distance is the radius. So yes, P, the circumcenter, is equidistant from these vertices because they're all points on the circle that P is the center of. All right, so down here, looking at CG and AG. Well, look at point G. First off, and it can start getting messy trying to recognize these things. So look at what I'm seeing here. Look through my eyes. What I'm seeing are the right angle marks and the congruent mark on either side. Now, if I just saw a right angle, that would not tell me I had a perpendicular bisector. I have to see the right angle and the congruence marks. So DB is a perpendicular bisector. Excuse me. DB may not be straight. Let's say DG is a perpendicular bisector. Because like, see how C to G, it kind of, G to here is different? They're not, not sure how best to show you this. Basically, if we continued CG, remember what I said about it not necessarily going through a point. So this is actually the perpendicular bisector. All right, so GD is a perpendicular bisector, GE is a perpendicular bisector, and G, no particular letter, right here, this is a perpendicular bisector. So point G is where they all meet, and that makes G the circumcenter. So G is a circumcenter. That's the first thing to recognize. And then you have the fact that circumcenters are always equidistant from the vertices. Well, what are the vertices? They are A, B, and C. So G to A, G to B, and G to C are going to all be the same. We're told here that G to B, and let me go ahead and say that. G to A, G to B, and G to C are the same because the circumcenter is equidistant from the vertices. We're told that GB is 2. Well, that means that GA is 2 and GC is 2, and that's what these are asking for. So GA has a length of 2 units and GC has a length of 2 units. All right, good time to pause the video and try these next two. Excuse me. All right, I'm going to go ahead. So if you have already paused, tried them, and are ready to move on, you're welcome to come with me. Again, I have 3 perpendicular bisectors. VS is a perpendicular bisector. VU is a perpendicular bisector, and VT is a perpendicular bisector. They all meet at V, so V is the circumcenter. The circumcenter is always equidistant from the vertices. In this triangle, that means P, R, and Q. So from V to P, V to R, and V to Q are all going to be the same. Well, they told me that V to P was 16. If V to P is 16, so is V to R, and so is V to Q. All right, next, name all congruent segments. Okay, so K to M is a perpendicular bisector, J to M is a perpendicular bisector, and L to M is a perpendicular bisector. So they meet at M, which means M is the circumcenter, sorry. We know that the circumcenter is equidistant from the vertices. Here are my vertices, F, G, and H. So, if I'm just naming congruent segments, I'm going to do it with segment names. MF is congruent to MG, is congruent to MH. Okay, because M, the circumcenter, is equidistant from the vertices. Is that all? No, we have a whole bunch of congruent segments that are already marked because of perpendicular bisectors. For JM to be a perpendicular bisector, it has to bisect FG. That's why FJ and JG are marked as congruent. So FJ is congruent to JG. What else? FK congruent to KH. What else? GL congruent to LH. And that covers all the congruent segments. Thanks for exploring perpendicular bisectors and perpendicular bisectors in a triangle with me. Now we know that the perpendicular bisectors meet at a point of concurrency called the circumcenter, and that it has the unique property of being equidistant from the vertices because it's the center of the circumscribed circle that goes through those vertices. See you later.